Well, this is an exciting one. Let's start by sketching triangle ABC at the given variable coordinates. I'm going to put B right here at HH. I'm going to put C over here at 2H0. So the figure is going to look a lot like this. Okay, let's see what I can make out of this. Now, I can calculate the length of AB. Now, I'm using this distance formula here, but I know I've mentioned the distance formula this way, the delta or change notation, change in x, change in y. From A to B, the change in x is h. The change in y is also h. So h squared and h squared, 2h squared. And if you're not good at this, you'll get there pretty soon. We have to know how to deal with those radicals. So this has a distance of h times radical 2. Well, let's do the same thing for the other side. And as you'd expect, it's actually the same thing. Because the distance for this segment from h to 2h is a distance of h. And the vertical distance is a distance of h as well. So the same thing, 2h squared, I'll take the square root of that, and I can separate that into h radical 2. Now at any point, you could have compared. You didn't actually have to simplify it this far. Let's suppose you got this far over here, and you got this far over here. You know they're equal, and that tells you this, that ABC is isosceles. So that's what we've got so far. We've got an isosceles triangle on our hands. But as the saying goes, but wait, there's more. Let's look at this. The slope of AB is clearly 1. So I'm just going up h over h. Now the slope of BC, clearly negative, down h over h. And that is also going, well, that will be a slope of negative 1. And therefore, these two slopes are opposite reciprocals. 1 and negative 1. Opposite reciprocals, that makes angle B a right angle. So the triangle is isosceles, and I've got a right angle. So this is an isosceles right triangle. Well, let's plot these points for A, B, C and see what kind of triangle we have. I'm given the coordinates 0, n, and again, m and n restricted to positive values. It's got to be on the y-axis. After all, it looks like a y-intercept. Let's go over to point C, m0. Coordinates of m0 clearly on the x or horizontal axis. Now, I can imagine a point here. mn will be vertically aligned with C, horizontally aligned with A. Well, if you don't see that, let's draw this. Again, look at this line. This is a horizontal line because it has a constant value, y value, of n units. This vertical has a constant x value of m units. So, if I want to know slopes, this slope, horizontal line, again, the difference of the y's, change in y is 0, so that has a slope of 0. The vertical slope has a change in x of 0. Division by 0 is undefined, therefore the slope is undefined. A vertical and horizontal line form a right angle on the coordinate plane, and that gives us a right triangle. And one last bit of trivia. To travel from A to C, I would have a decrease of n in the vertical direction and an increase of m in the horizontal direction, or a rise of negative n over a run of m. So the slope of AC is negative n over m. Okay, number 29 here. Let's see if we can first find the coordinates of this point here, P, in red. I'm going to start by checking out this y-axis. I know when a point is on the y-axis, such as the origin, the value of x, the abscissa, is 0. So it's going to be 0, comma something. Well, I know that this line, I also see a horizontal line here where all points for y are equal to k. 2h comma k, hk. So this orange line, horizontal line, is the line y equals k. So no matter where I am on this line, k, k, k. Pretty straightforward. So let's just fill in the blanks here. I know that these lines, I've got a horizontal line. Put that line back there for a minute. Horizontal line and a couple vertical lines. And that means I'm going to generate right angles. And now I'm looking at this. I know the distance here between R and S is a distance of k. A distance from Q to S is a distance of h. From h to 2h. In this case, from k to 2k. And I can see that the same is true down here. From 0 to k, a distance of k. And this horizontal distance from 0 to h is a distance of h. So I would say these two triangles, we've just demonstrated congruence by side, angle, side. And of course we could have done it with side, 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 but this looked a lot easier. Well, let's make some use of these variable coordinates in this diagram of triangle ADE, which is isosceles, and we're going to demonstrate that these two segments, or the lines containing them, have slopes that are opposites. We first need to find the coordinates of G and H respectively. Remember, they're variables. We don't really know the true shape of this figure, nor does it matter. So let's start by finding the coordinates of the red and the green point respectively. Remember, you've got this fancy pants formula there, but that's so boring. Just take the middle. What's in the middle of negative 2h and 0? Well, it's pretty obvious. It's going to be negative h. The middle between 0 and 2k is k. Now you can see why someone chose the negative 2h and the 2k for the variable coordinates, because it gives you a nice convenient midpoint. So doing the same thing over here on G, just in the positive. The average, if you will, of 0 and 2h is h, 2k and 0 is k. Easy said and done. So that takes care of this formula. Now, let's work on some slopes. I'm going to find, I could take the green slope, clearly positive, or I could represent it this way, up and over. Remember this? And I could click on this and it says up k, because I'm starting at 0, going to negative hk, and I'm going over 3h. I'm at negative 1h here, and I'm sorry, negative 2h to here makes 2h and one more h. That's a distance, a run, if you will, a horizontal distance of 3h. Or I could just plug in the formula just like that if I want to do it the old school way. So let me clean this up a little bit. And I know my slope is going to be k over 3h. So that's the slope of the green line. And we're going to say that's a positive slope. So for the red line, HE, it looks like it's descending, and it sure does, down k over 3h. So I could represent it that way, or I could just go through this formula, and there you go. I look at these two slopes, and I've got k over 3h, and that's its opposite is negative k over 3h. Nicely done. And remember, we don't know what this figure looks like because the coordinates, after all, are variable. Well, here we go with a coordinate proof. Given this diagram, and we got the points here we have to plot, and the distance formula, we are going to use this algebra to demonstrate that two sides have the same measure, making the triangle isosceles. So let's plot them. I know that P is on the y-axis. I know that Q must be on the x-axis. And given the coordinates of R it's on the opposite side of the y-axis from point Q. Okay, all right, looks pretty good so far. So my triangle looks like this. And I'm trying to demonstrate that this is isosceles. So let's have a look. I'm going to use my distance formula. I'll take this right here. And I'm going to say, I'm looking right here. This is my x1, y1, x2, y2. The 0 minus the negative h. And for the y's, k minus 0. And I'll just work that out. And I come up with square root of h squared plus k squared. Straightforward. Now let's try PQ. It's going to be this side. And I customarily choose on the left x1, y1, x2, y2. So now I've got h minus 0 for the x. I'm going to square that quantity, and 0 minus k for the y's. And if I work that all out, what do you know? I'm going to get the same thing. Of course, 0 minus k, negative k squared, is in fact positive. So I could only conclude from all this that since these two measures are equal, two sides are congruent, and therefore the triangle is isosceles.